Welcome back to part 2, section 14.1. So number 22, rapid drainage of floodwater is crucial to prevent damage during heavy rains. Several designs for a drainage canal were considered for a certain city. It looks like 5 different types of designs were considered. Each design was tested 4 times. There may be a typo in your book. It should be only 4. There's only 4 pieces of data for each of the different types of channel. So I've corrected it here. Each design was tested 4 times to determine how long it took to drain the water in a reservoir. The following table presents the drainage times in minutes. So we'll skip part A. We're not doing anything with the table. So letter B, can you conclude that there is a difference in the mean drainage times for the different channel designs? Use the alpha equals 0.01 level of significance. So we'll write up the test in just a moment, but what you want to do here is pause the recording if you would, and you need to get all this data into your calculator, and you're going to do it lists and in lists. So the first data, the 4 values of data there, that first row is going to go into L1, and then the next row into L2, and L3, L4, and L5. So if you would, pause the recording and go ahead and put those numbers into your 5 lists, reading across those rows. Then, once you've got your numbers into your 5 lists, you're going to hit the Stat button again and go over to Tests, like we know how to do, and then you might actually scroll up because the test that you want is ANOVA, and it's the very last one in the list. So if you scroll up, you get to it faster. And then we all do this the same way. You have to tell the calculator to use the 5 lists. So you're going to go L1, comma, L2, comma, L3, comma, L4, comma, L5. And the comma button is above the 7 button. It has its own button. So look above your 7 button and you should see the comma button. All right, and so once you run that, you're going to see a bunch of stuff, test stat and p-value and so forth. So let's write up the test now to the right here. So the null hypotheses would be that the 5 drainage times are all the same. So mu1 equals mu2 equals mu3 equals mu4 equals mu5, all right? And then the alternative would be that at least one mean time is different. And then we could look more closely to see if we think it's more or less than the others. All right, so 3 or more means that we're going to use this new F distribution, which I admit is pretty mysterious at this point. Distribution, because I'm not talking about it much, but it is a different distribution. You could also just say that it's going to be ANOVA, and that would be sufficient. And no critical value for us. It's just too much to try to get it. So we're not going to worry about it. But it's a little bit like the chi-square distribution, where if we were to calculate, the F distribution looks a lot like the chi-square, and we would be looking for that reject zone in the right tail. And we're just not going to worry about that critical value. All right, so that's our hypotheses, our distribution statement, and then we do our calculations. So you could say data into lists, and then we run ANOVA, and then we get our test statistic, which always good to label it. The test statistic is F equal to 9.2357, take it out 4 places. And then the p-value, careful, we've got something tricky on the calculator. It looks like 5.7 or so, but then way out there we've got that e to the -4. So that means we're going to rewrite that as we move the decimal point left 4 places. So 1 place past the 5, 2, 3, 4. So that would be 0.00057. So what looks like a really big number is actually quite small. So then as we do the comparison, we only have the p-value to the significance level, so 0.00057 compared to the given 0.01, and our p-value is definitely small. So that means we're going to reject the null, When the p-value is low, the null must go. And at the 0.01 significance level, we can conclude that there is a difference in the mean drainage times. So that's what I've written out here. And now notice this doesn't tell us which one, like which one is higher, which one is lower, that kind of a thing. We'd have to go back and inspect these rows of data. And just looking across the rows, I'm seeing that number 4 seems to have a lower numbers overall. And if we're looking at drainage times, we want low numbers. We want things to drain quickly and not take very long. So I would guess that number 4 is a significantly lower one. Number 3 is not doing too badly. And the other ones look like they're noticeably higher. So there you have an example of a hypothesis test with ANOVA and sort of an abbreviated test. We've got one last quick example here where we're going to read from a table. So number 30, high levels of phosphorus in soil can lead to severe reductions in water quality and animal populations. Investigators treated soil specimens with 6 different treatments, and the acid phosphatase activity, which is related to the production of phosphorus, was recorded. And presumably we want low amounts. Results are presented in the following one-way ANOVA table. The units are micromoles of phosphatase per gram per hour. So you'll notice we have our 6 different treatments, A, B, C, D, E, F, and here in the treatment row, which is also known as the factor row, our calculators say factor. This software says treatment. Right there, this number 5, that's our n-1. So that's how we know there were 6 treatments. And then the error number there, that's measuring the variation within the samples, kind of saying, are these reliable samples, are these less reliable samples, that kind of a thing. So we're just going to quickly grab the value of the test statistic in part C. Again, I'm skipping some of the parts. So that number there labeled F is our test statistic. So 46.64. I don't have a sense if that's big or not. But what's important is the p-value, which over here is labeled capital P. That's our p-value. So can you conclude that the mean level of acid phosphatase activity varies among the treatments? Use the alpha equals 0.05 level of significance. So remembering that the null is that they are all the same. So here I am writing it in words. The means are all equal. The alternative is that at least one mean is different. Okay, and since we're not doing the full calculation and all this stuff, we didn't do any calculation on our own, I'm just going to jump right to the comparison. Elsewhere, I do ask you to write out, the full hypothesis test, but here in this very last section, I'm letting you get away with a lot less. So we're going to grab the p-value, which is essentially 0, which is certainly less than alpha equals 0.05 or any other alpha they might care to give us. So we have a low p-value, so we would say at the 0.05 significance level, we can conclude that there's a difference between the level of acid phosphatase activity. Oh, so you know what I forgot? Maybe you caught me. I forgot to say reject the null. So do always make that statement about the null hypothesis. And then your second statement, remember, is about the alternative, which is that something is different. So at the 0.05 significance level, we can conclude the mean levels vary among the treatments. And there I was trying to just grab the language of the question. Do the mean levels vary? And they do. And that, my dear students, is the end of our material. Well done.